When connecting a generator to multiple buildings, specifically a house and a detached garage, each with separate meters and service entrance disconnects fed from a common utility transformer, and with the generator not being a separately derived source where the frame is connected to a grounding electrode but lacking a bonding jumper between neutral and ground, there are critical grounding considerations. The goal is to connect the generator output to both buildings via separate transfer switches, and these transfer switches have unswitched neutrals. Connecting the generator neutral to both buildings via a bus bar would effectively connect the neutrals of both buildings. To address this, the main bonding jumper, referred to as MBJ, between the grounded conductor, meaning the neutral, and the grounding electrode, must be disconnected, and one of the service entrance disconnects to isolate the neutral in one panel. The plan should involve tying all equipment grounding conductors, including those in both service entrance panels and the generator frame, together. The primary concern is preventing circulating currents. These currents can flow through neutral and grounding conductors if there are multiple neutral to ground bonding points within the system when the generator is operating. When a generator is connected to a system with multiple grounded conductors, it is essential to ensure that there is only one point of reference for the neutral. Transfer switches are often used to isolate the generator's neutral from the utility system's neutral. However, if the transfer switches have unswitched neutrals, the neutrals of both buildings become connected when the generator is running. Therefore, disconnecting the MBJ in one of the service entrance panels is crucial to prevent these circulating currents. Here's a detailed step-by-step outline of the process for safely connecting the generator to the two buildings while ensuring proper grounding. Firstly, connect the generator output to both buildings via separate transfer switches. Ensure that these transfer switches are appropriately sized for the load and are installed according to local electrical codes. Secondly, tie all the equipment grounding conductors from both service entrance panels and the generator frame together. This creates a common grounding system that provides a low impedance path for fault currents. This connection is vital for safety, as it helps ensure that any fault currents are quickly cleared, reducing the risk of electrical shock. Thirdly, disconnect the main bonding jumper in one of the service entrance disconnects. This step is essential for isolating the neutral in one of the panels and preventing circulating currents. By removing this bonding jumper, you are ensuring that there is only one neutral to ground connection point in the system when the generator is operating. Fourthly, connect the generator neutral to both buildings via a bus bar in a junction box. This bus bar serves as a common connection point for the neutral conductors from the generator and both buildings. It ensures that the neutral is properly distributed to both buildings while maintaining the integrity of the isolated neutral system. By following these steps, you can safely connect the generator to both buildings and prevent any potential circulating currents. This approach ensures that the electrical system operates safely and efficiently when powered by the generator. Understanding the NEC, National Electrical Code, requirements is important. The NEC provides guidelines on grounding and bonding to minimize electrical hazards. When connecting a generator to multiple buildings, these NEC guidelines should be followed, particularly those related to grounding and bonding requirements in Article 250. The NEC addresses requirements for grounding and bonding of electrical systems, including those with generators. Proper grounding and bonding are crucial for electrical safety, ensuring that fault currents can safely return to the source and activate overcurrent protection devices like circuit breakers or fuses. Article 250.24 covers grounding service supplied alternating current systems. It requires that the grounded conductor at the neutral be grounded at the service equipment. However, in situations with multiple buildings supplied from a single generator, modifications to this general rule are necessary to prevent circulating currents. Section 250.30 details grounding requirements for separately derived alternating current systems. A separately derived system, such as a generator with a bonded neutral, requires its own grounding electrode system. However, in this scenario, the generator is not a separately derived system, and therefore the grounding approach differs. Article 250.32 addresses grounding requirements for separate buildings or structures. It allows for the grounded conductor to be connected to a grounding electrode at the separate building or structure. However, it also specifies conditions where this connection must be omitted to prevent parallel paths for neutral currents. This is relevant to the scenario where the generator is connected to multiple buildings. Following these sections of the NEC is critical for ensuring a safe and code-compliant installation. Specific steps to take when connecting a generator to multiple buildings include the equipment grounding conductors. These must be connected from the generator frame to the grounding electrode systems at each building. This provides a lower impedance path for fault currents. The size of these conductors must comply with NEC Table 250.122, which specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. Secondly, one building must have the main bonding jumper removed at its service equipment. This ensures that there is only one neutral to ground connection point in the entire system, preventing circulating currents. The location where the bonding jumper is removed should be chosen based on convenience and accessibility. Thirdly, the neutral conductor from the generator must be connected to the neutral bus in each building's service equipment. This connection must be made through a transfer switch to allow for seamless switching between utility power and generator power. The transfer switch should be rated for the full load of the building it serves. Additionally, all metal enclosures and raceways must be properly bonded. This includes the generator enclosure, the transfer switch enclosures, and any metal conduit or cable trays used to route conductors between the generator and the buildings. Bonding these metal parts together ensures that they are at the same potential, reducing the risk of electrical shock. Grounding electrodes must be installed at each building. These electrodes can be ground rods, ground plates, or metal underground water pipes. The grounding electrodes must be connected to the grounding electrode conductors, which in turn are connected to the grounding bus in the service equipment. The size of the grounding electrode conductors must comply with NEC Table 250.66. The grounding electrode system provides a path for fault currents to return to the source and helps stabilize the voltage to earth. Understanding circulating currents is essential. Circulating currents, also known as parallel neutral currents, can occur when there are multiple neutral to ground connection points in an electrical system. These currents flow through both the neutral and grounding conductors, which can lead to several problems including increased energy consumption, overheating of conductors, and nuisance tripping of circuit breakers. The main cause of circulating currents is the presence of multiple paths for neutral current to return to the source. When the neutral is bonded to ground at multiple locations, the current will divide and flow through all available paths. This can result in some of the current flowing through the grounding conductors, which are not designed to carry normal load current. Removing the main bonding jumper at one of the buildings ensures that there is only one neutral to ground connection point, eliminating the possibility of circulating currents. In the scenario, the generator is not a separately derived system. This is important because the grounding requirements for separately derived systems differ from those for non-separately derived systems. A separately derived system is one where the power is derived from a source that is electrically isolated from the utility supply. In this case, the generator is connected to the existing electrical system and the neutral is not isolated from the utility neutral. This means that the grounding requirements are governed by the rules for non-separately derived systems. These rules require that there be only one neutral to ground connection point in the system. Transfer switches play a critical role in safely connecting a generator to a building's electrical system. Transfer switches are designed to switch the building's load between the utility power and the generator power. They also ensure that the generator is properly isolated from the utility grid when it is operating. There are two main types of transfer switches: manual and automatic. Manual transfer switches require the user to manually switch the load between the utility power and the generator power. Automatic transfer switches automatically switch the load to the generator power when a power outage is detected. When using transfer switches with unswitched neutrals, it is essential to disconnect the main bonding jumper at one of the buildings to prevent circulating currents. The transfer switches should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or UL. The transfer switches must be rated for the full load of the building they serve. Consider the load calculations when selecting a generator and transfer switches. Proper load calculations are essential for selecting the right size generator and transfer switches for the application. The load calculation should take into account all of the electrical loads in the building, including lighting, appliances, and HVAC equipment. The generator should be sized to handle the total load with some extra capacity for future expansion. The transfer switches should be rated for the full load of the building they serve. It is always a good idea to consult with a qualified electrician to perform the load calculations and select the appropriate equipment. Safety is paramount when working with electricity. Always follow safe work practices and wear appropriate personal protective equipment (PPE), such as safety glasses and gloves. Never work on electrical equipment while it is energized. Always de-energize the circuit and verify that it is de-energized before working on it. Follow all applicable electrical codes and regulations. If you are not comfortable working with electricity, hire a qualified electrician to do the work. Periodic inspections and maintenance are essential for ensuring the continued safe and reliable operation of the electrical system. The generator should be inspected regularly for any signs of damage or wear. The transfer switches should be tested periodically to ensure that they are functioning properly. The grounding system should be inspected to ensure that it is intact and providing a low impedance path for fault currents. Any problems that are found during the inspection should be corrected immediately. In summary, when connecting a generator to multiple buildings with separate meters and unswitched neutrals, it is important to disconnect the main bonding jumper and one of the service entrance disconnects to prevent circulating currents. This ensures that there is only one neutral to ground connection point in the system. Follow the step-by-step process, which includes connecting the generator output to both buildings via separate transfer switches, tying all equipment grounding conductors together, disconnecting the MBJ in one service entrance disconnect, and connecting the generator neutral to both buildings via bus bar in a junction box. Following these steps will ensure a safe and efficient electrical system when powered by the generator. Always consult with a qualified electrician to ensure that the installation is done correctly and complies with all applicable electrical codes and regulations. Load calculations are necessary to ensure that the generator and transfer switches are adequately sized for the application. Regular inspections and maintenance are essential for ensuring the continued safe and reliable operation of the electrical system. Always prioritize safety when working with electricity. The key to a safe and efficient installation is a thorough understanding of grounding principles, NEC requirements, and the proper selection and installation of equipment. By following these guidelines, you can safely and reliably connect a generator to multiple buildings and provide backup power when needed.